Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 16 of chapter 1, that is transformers. So today we will discuss about testing of transformers. We will discuss about polarity test, open circuit test and short circuit test. And why are these tests very important and what are the purpose of each test. There is a purpose of each test. Also we will not cover the Sumner's test, okay? Load test, which is known as the load test or known as the Sumner's test. So that will be a ESC topic. So generally you can cover it from anywhere, from YouTube or somewhere. Okay, not this will not be asked in gate. Sumner's test will not be asked in gate. Okay, I also have forgotten the spelling. Sumner's test. Okay, so first let us discuss what is testing of transformer. So direct load testing on a transformer is not always feasible due to difficulty of arranging appropriate load and significant energy losses involved. What does it mean? So previously also I did discuss with you, right? When we were discussing about losses, there I told you that we actually do not load the transformer and measure the efficiency, correct? That will be very bad because I have to buy higher rating measuring instruments. I have to load the transformer to rate it. So if let's say I have a 100 kVA transformer, right? I have to load the transformer fully. So I have to find a load that consumes 100 kilowatt or something like that. Whatever is the power factor, 100 kilowatt if the power factor is assumed to be unity. Okay, so I have to find a load which actually consumes 100 kilowatt of power. That finding that amount of huge load, right, is a big task. That is very costly. Then again, loading that will be very costly because there will be losses of huge, right? 1 kilowatt of copper losses, 1 kilowatt of coal losses. There will be huge losses. So measuring those also will be very difficult. So we never actually load the transformer and then test, right, the efficiency. We never do it actually. That is not a very good method of testing. So what we do, we find the parameters of the transformer. So in the equivalent circuit, if you remember, we have the parameters as RO1, then R2, then I have the parameter X1, then X2, like this, right? The leakage reactance XL1, XL2, then I have this R core resistance and the magnetizing reactance. All these things were there. So we will actually find out these parameters and through this we will model the equivalent circuit. And as I have the parameters, if I know the parameters, right, of this circuit, if I am able to find out, this is, let's say this is RO1, XO1, this is my R core and XM. Okay, so if I am able to find out the parameters, that means I will easily be able to model the losses, because what will be the copper loss? Copper loss will be I square into R1, right? So at any load, it does not matter because current will, I will choose the current. If I know R1, I will be able to model the copper loss at any load. If I know the R core, I will be able to model the coal loss. Coal loss will be what? It will be V upon the R core, V square upon R core. This will be the coal loss. So I am able to model the loss at any load. It does not matter. Okay, that is the advantage. So our purpose will be to find out these parameters. So these parameters are found out with open load, open circuit, that is no load, or short circuit test. Okay, before that we will study about polarity test. So what is polarity test basically? So polarity test is used to determine the polarity of primary and secondary windings. I mean the instantaneous polarity. Basically whatever we were discussing, that writing the dot convention without actually seeing the winding orientation, can I determine the polarities? There is a test known as polarity test. Okay, it is essential for parallel operation to ensure correct phase relationship and prevent circulating currents. Why? What do we mean by parallel operations? What do we mean by parallel operations? Okay, so what do we mean by parallel operations? So if you ever want to connect, like let's say this, I have a voltage source here. This is the basically best example. I have a 100 volt voltage source. if I have a 100 volt voltage source and this voltage source at max can send 5 amperes of current, it cannot send 5 amperes of current. I have a load that actually operates in 100 volt, but it is 1 kilowatt load. So what is the current requirement? So current requirement I will be 1 kilowatt by 100, that is 10 amperes. So load requires 10 amperes of current, but I have a supply that only can send at max 5 amperes of current. So how will I calculate this? So basically I will go to the market and bring another, of course there is another option that I buy a 100 volt 10 amperes of supply that can supply 10 amperes, or I can buy another 100 volts 5 ampere that can provide maximum 5 amperes of current, and I connect those in parallel. If I connect those in parallel, what will happen? So if I connect those in parallel, and let's assume that source has some source resistance, so this will be source resistance, okay, RS2, and here is my load. Basically load is somewhere here. Okay, so what will happen is I do agree that yes, there will be some drop here, here will be some drop, here will be that some drop, due to which the voltage here exactly won't be 100, but very close to 100 it will be here. So this will supply 5 amperes of current, this will supply 5 amperes of current. Okay, so that's how parallel operation is very useful. So transformer also, if the rating of the transformer is 100 kVA and I have a load of 200 kVA, so I can connect two transformers in parallel of 100 kVA rated, so that both together can supply the power or the energy. But what is the problem? You said there is a problem. The problem is, if by any chance this positive terminal is not connected with positive, there will be huge problems. What kind of problems? So if I connect this in opposite orientation, so now if I apply a KVL in this loop, right? If I apply KVL in this loop, this will be some current IS1, this will be current IS2. Okay, so if I apply KVL in this loop, this will be 100 minus IS1, sorry, this will be 100 and this will be plus IS1 into RS1. I'm just applying KVL in the loop, then it is minus IS2 into RS2 plus 100 equals to 0. So this will be basically IS1 into RS1 will be equals to IS2 into RS2, and okay, this is the value. Basically this is the drop, and my IS1 and IS2 will be very small actually. Yeah, like this is the first equation if they are in same polarity. Okay, now if they are connected in opposite polarity, what will be the problem? If they are connected in opposite polarity, what will be the problem? If they are connected in opposite polarity, let's see. So I will copy this circuit and I will apply the same minus plus. Okay, now what will be the problem? Now the problem is that this is minus 100 plus IS1 into RS1, and this is this is minus IS2 into RS2 minus 100 equals to 0. So now, right, what is happening is IS1 RS1 minus IS2 RS2 is equals to 200 volt. What does it actually mean? What does it actually mean? This basically means that this drop, right, like here. So for a second, if I assume that RS1 equals to RS2 equals to RS. So here my IS1 will be equals to IS2, that is fine. So it will be equals to 5 amperes, because here, right, 10 amperes needs to go, right, 10 amperes needs to go. So if I apply KCL at this node, my IS1 plus IS2 will be equals to 10 amperes. So from here IS1 and IS2 are equal, so IS will be equals to 5 amperes. Okay, now here again they needs to be equals to 10 amperes, and let's assume that RS1 and RS2 are same. So it is basically RS into IS1 minus IS2, okay, equals to 200. Okay, and for a second let's assume that like the source resistance is generally very low value. Assume it has equals to 1 ohms only. Okay, I will choose other values. Okay, I will choose other values as well. So if I assume the source resistance to be 1 ohm only, so this will be IS1 minus IS2 equals to 200 amperes basically. And also if I apply a KCL at this node, load will consume 10 amperes only, right? So IS1 plus IS2 equals to 10 amperes. So from here I can directly say that IS1 will be equals to 200 and 105 amperes, and your IS2 will be equals to, sorry, hold on a second. So if I add these two numbers, this will be 210 divided by 205. Yes, this is correct. So what will be IS2 equals to? IS2 will be equals to some negative number. Okay, IS2 is equals to, so, minus of 95. Can you just imagine like what is the current here, right? My battery does not even support this. Okay, just imagine what is the current. 95, like magnitude, I'm talking about magnitude. 95 amperes of current is flowing, 105 amperes. So if you increase the RS, the current will reduce, but practically, right, RS, the source resistance is generally very low. Source resistance is generally very low. So like the problem was that my voltage source was not able to send enough current. So that's why I connected two voltage source in parallel. But you superimpose the problem. So you connect them in opposite polarity. If I connected them in opposite polarity, what happened? The current that they are supplying is very high. But you will say, sir, load is only taking 10 amperes of current. So what is happening? So this, right, this current is actually the circulating current, that is circulating from here to here. IC, known as the circulating current. So there are two currents. One is the current that is flowing here. Another one is the circulating current that is going in the supply, because there is potential difference here. Previously there was zero potential difference, both were at 100 potential, so no potential difference. Now there is potential difference. So circulating current flows, circulating current. So that's a huge problem, right? Huge problem. 100, can you imagine 105 amperes? Your battery can only support 5 amperes, but like circuit is telling me 105 amperes will flow. That's a huge problem, right? So of course, to mitigate this issue, we have to connect dot with dot, right? We have to connect with the same polarity. If I don't connect with the same polarity, then this disaster will happen. Okay, this disaster will happen, which we definitely don't want. Okay, so that's why it is written over here why polarity test is important. When connecting two transformer in parallel, the corresponding terminals must have same polarity to avoid the circulating current and potential damage. It is crucial in applications such as voltage addition and subtraction. Okay, so how is the polarity test performed? So we identify the terminals of the transformer that have same polarity on primary and secondary with voltmeters. Okay, ensure correct connection when transformers are connected in parallel operation in phase sensitive operations. So what we will do, like our circuit diagram, test circuit diagram will be somewhat like this. Okay, so we will have three voltmeters, VA, VB, VM. Okay, and these 2 points will be shorted. So the reading of the voltmeter will depend whether it is shorted with dot or not dot. Okay, so let's assume first that it is connected with a dot. Okay, if it is connected with a dot, then what will be the reading basically, what will be the reading. So if it is connected with the dot, okay, so let's assume there are two cases, right? So I will copy this circuit. There are two cases. So this is the arrangement, my experiment arrangement. Okay, so what I can do, let's assume the case one where actually the shorted terminals both are dot. So this is dot, this is also dot. So if both of them are dot, that means this will be some VA potential, okay, Vn, and this will be the VB potential, right? So it will be plus here minus, it will be plus here minus. So this will be plus minus VA, this will be plus minus VB. Okay. So now what will be the voltmeter reading basically? I want to measure the voltmeter reading. Okay. So the voltmeter reading is always like this. Okay. Voltmeter is connected like this. So this is the higher potential, this is the lower potential. Okay. So now if I just apply a KVL in this loop, if I apply KVL in this loop, what am I observing? That minus of Vm, that is the voltmeter reading, minus of Va plus of Vb equals to 0. Okay, so I get my voltmeter reading to be Va minus Vb. So if the two dots are shorted together, that means the voltmeter reading will be the difference of these two voltages. Okay, so it will be lower, it will be lower value. Now for case 2, if the two dots are not shorted with each other, okay, if the opposite is happening, the voltage will be very high basically. Case 2, if this is dot and this is dot here, so dot with come with positive, so this will be now minus plus Vb. So I do understand, yes, it is AC circuit, yes, I do understand that, but we are talking about instantaneous polarity. So at a particular instant, if this is positive, this should be positive according to the dot notation. Okay, according to the dot notation. Okay, so I can directly say here that again if I apply the KVL, this will be minus Vm minus Va minus Vb equals to 0. So Vm is equals to Va plus Vb. Okay, so Va is equals to Vm plus Vb. So I hope you understand this point, that if, like, this is the reading of the voltmeter. So if dots are not connected, then the reading of the voltmeter will be additive in nature. Yeah, sorry for the interruption, like my recording got crashed. So what I was saying is basically the reading of the voltmeter will be additive in nature, if it is not actually, if the dots are not shorted properly. So if dots not shorted properly, okay, and here it will be subtractive in nature, if I know the connections are proper. Okay, so that is what is written in the conclusion itself, that types of transformer polarity, it will be additive polarity, both the secondary and primary, like the voltmeter reading will be addition of both the values if the windings are connected in opposite fashion. Okay, the voltmeter is connected across the terminal of opposite polarity, then it will read the addition, and if it is properly connected, then it will read the subtraction. Okay, here it will read subtraction. When primary and secondary polarities match, the voltmeter reads E primary minus E secondary. Okay, so the voltmeter is connected across the terminal of same polarity. Okay, so yeah, that was about the polarity test, and this is the procedure of polarity test, that we connect low voltage AC supply in the primary winding, we connect a voltmeter between a selected primary terminal and the secondary terminal, and we short the other two terminals. Okay, and then we observe the reading of the voltmeter. If it is additive, that means the connection is, if the reading is higher than the primary voltage, that means it is additive polarity, because what is my reading? Vm either will be V primary plus V secondary, or it will be the difference. Vm will be the difference of V primary minus V secondary. Okay, like RMS value, if V secondary is higher, then it will be negative, I do understand, but we are talking about RMS value. Voltmeter measures the RMS value. Okay, so if it is higher than the primary voltage, if it is higher than the highest voltage, applied voltage, that means it is additive polarity, that means the connections are wrong. If it is lower than the applied voltage, that means the connections are proper. Okay, got it? Yeah. So then you can label the transfer terminals. Okay, so these are the applications, and one interview question of this polarity test: how does polarity test of transformer windings affect the phase relationship between the secondary and primary voltages? So the polarity test of the transformer windings determines the phase relationship between the input and output voltages, because we want, when input voltage increases, output voltage should also increase, then only dot will be connected to dot. So the phase difference between them will be 0. So that is what it is telling, that if they are in phase, if they are in phase, if the both this dot is in here, if the connections are proper, they will be in phase, else they will be out of phase by 180 degrees. So if this is increasing, then the voltage in the second coil will decrease basically. Okay, so here, right, if the windings have additive polarity, that means it is, sorry, it is opposite phase connection. If they have additive polarity, that means it is opposite phase connection. It is written wrong here, it is opposite phase connection. Opposite phase connection. And if they are having subtractive polarity, that means they are in the same phase connection. Or in phase or same phase, that is basically 0 degree. Opposite means 180 degree phase. Okay, got it? Okay, this also will be 0 degree then, will be 0 degree. Okay, this, right, okay, that is unfortunate. This will be 0 degree actually, a lot of things have to change. 0 degree, and this will be out of phase with primary, with secondary, no, sorry, with primary. Okay, so that's why correct polarity is very crucial, okay, to find out this phase difference. So one question came in gate, so let's solve this question. So this, I think we guess, I guess we have solved this previously as well. Again I will solve. Okay, so here a 400 volt 200 volt windings are shown, connected as shown. The reading of the voltmeter will be, okay, okay, the dots are not present. I forgot to write down the dots actually. So yeah, dots should be present in the question. So one of the dots should be here, and I will just see in my notebook where is the dot. The other dot is here, and the other dot is here. Okay, so these are the dots basically. So yeah, now you can solve it. So we actually had solved this previously, so now again we will solve it. So we have to find out the voltage. So if I copy this circuit across the voltmeter reading across the, sorry, voltage reading across the voltmeter, so this will be here. Okay, so this will be plus minus V here, voltmeter reading, and this will be higher if dot is plus minus, this will be plus minus, this will be plus minus. Okay, and so how will the KVL work? KVL will, I will start from here, go through the connections and end here. Okay, this loop. So this is how much? This is 400 volts, right? Because input is 400 volts. This is 200 turns, so this will be 200 volts. This will be 200 volts, and this will be again 200 volts only because the turns is 200, but in opposite direction. So if I apply the KVL starting from here, so it will be minus of V, minus of 200, minus, so I will always take the first sign that I encounter, minus of 200 plus of 400, first sign that I encounter, equals to 0. So voltmeter reading is 0. So very basic questions on polarity test will come. Now let's discuss about open circuit test. What is open circuit test? So open circuit test is used to determine the no load losses or the iron or coal losses. Why? How so? So if I have the equivalent circuit, do I have the equivalent circuit? No, I don't have the equivalent circuit. So I will have to take it from the previous lectures. So okay, it is not here, it is not here. Where is the equivalent circuit, man? So yeah, here it is. So if the circuit is operating at no load, that means my I2 dash will be simply 0 because there is no load, right? It is open circuit. So it will be open circuit basically. No load. So what current will be supplied? Basically only I0 current. So my I1 will be equals to I0 only. Now you might have a doubt, sir, there is still winding loss, right? There is still winding loss, copper loss here. That is I0 square into R1. I will say yes, you are correct. Yes, you are correct, but that will be very low because your I naught, right? I naught is what? I naught is basically I current whole square plus Im square, and you know, like if your transformer rating is like 100 amperes or 10 amperes, your magnetizing current roughly hardly will be 0.5 amperes. IO current hardly will be 0.5 amperes. Generally it is 2 to 3% or 5% of the rated current. Okay, so this loss, yes, there will be loss, there will be some copper loss, but that will be negligible. We can neglect it. So ultimately what loss I will get? So we can neglect this drop as well. So what is the drop? So here, right, my E1 equals to drop of V1 minus like whatever is this equivalent impedance, like I into I1 I naught into Z, right, whatever is this impedance. But I have already told you that Z, this IO will be very low. So if this IO is very low, roughly, right, we can approximate that E1 will be roughly equals to V1 only. Okay, that is my approximation. So if E1 equals to V1 at no load, I will be able to calculate this V1 whole square divided by Rm. This will give me the coal loss. Okay, this will give me the coal loss, V1 square divided by Rm. That is what I want, right? V1 square divided by Rn is the loss in the core due to the eddy current and hysteresis loss. This we have already discussed previously. Okay, so that is my main objective. Okay, that is what is written over here. So it is used to determine the no load losses, iron loss or coal loss, shunt parameters of the equivalent circuit like magnetizing reactance. This also we will find out Xm, and the shunt resistance, core resistance Rm. Okay, connected on the LV side. So supply will be connected on the LV side. Okay, why will supply be connected on the LV side? I will discuss. Later on, I will discuss why supply will be connected on the LV side. Okay, requires low rating voltmeter and low voltage supply, making the test easier and safer. So there are two options, right? So this is my transformer. This is my transformer. So let's assume that this is my HV side and this is my LV side. So there are two options here. Either I can connect the supply in these two windings, or I can connect the supply here, and this I leave as open. Why am I choosing LV? Because power, right? Power is constant. If it is in the primary, it does not matter. Power loss or power, if it is in the primary or if it is in the secondary, it will be same. We have already discussed about this. So power does not change. And if I calculate the power in the low voltage winding, whatever P core I will calculate, that will be same as the high voltage winding. But what will be the advantage? In case of low voltage winding, let's assume this is 230 volts and let's assume this is 115 volts. So in case of low voltage winding, I just need to apply 115 volts. So that will be easier for me. And my instruments also, voltmeter, ammeter, voltmeter instrument also will be lower rating, because if I had to conduct the test in the high voltage, the instrument rating has to be 230 volts. Right here, the instrument rating has to be just 115 volts. That's it. Okay. So I hope you have understood this point. That is the only thing that is the reason actually why we perform this test on the low voltage winding and not on the high voltage winding. Okay, because remember here, right, my P core is dependent on voltage. Okay, and this voltage is rated, so I have to apply rated voltage. I cannot apply voltage like 10 volt, 20 volt. No, I have to apply rated voltage, because in the actual transformer we will work in rated voltage only, either 230 volts or 115 volts. So that's why I have to apply rated voltage. So I will choose the option in which I have to apply lowest voltage. Of course I have to apply rated, but in which option I have to apply the lowest voltage? LV side. If I apply a voltage in the LV side, I have to apply the lowest amount of voltage. Okay, got it? Okay. So we make the high voltage side open, and the low voltage side we apply the supply and connect the voltmeter and the ammeter and the wattmeter. I will discuss about what is the circuit connection. Okay, the circuit connection will be there just in the second 2-3 slides after. Okay, don't worry about it. Don't worry about it. Okay, so the high voltage winding is left open, ensuring no load condition. A small no load current will flow, typically 2 to 6% of the full load current, due to which there will be negligible copper loss and voltage drop across the winding. We will neglect that. We will simply neglect that. Okay, so now let's start with the circuit diagram. What is the circuit diagram? So the circuit diagram of the test will be somewhat like this. So there will be this is my LV winding, this is my HV winding. So HV winding is kept open and LV winding is here. Okay, so this is my ammeter, voltmeter. So what will ammeter read? Ammeter will read the no load current. So reading of ammeter will be no load current. Reading of voltmeter will be the no load voltage or the rated voltage. Right? This is not VO. This can be written as VO, or this is simply V rated or something. Okay, and the wattmeter, like whatever power is consumed right now. Of course, load is not there. That power consumed will be due to the core only, core loss only. So it will be P core. This will be equals to the core loss. Okay, this power will be consumed due to the P core. Okay, now how do I find out the circuit parameters? So I will just copy this circuit, not cut, copy, paste it over here. So I know the voltmeter reading, I know the ammeter reading. I know, like if I copy this circuit again. So what I know, what is my IO? IO will be 2 to 6%, right? So IO I know, okay, and this voltage V1 also I know. So all this I'm actually ignoring. All this I'm ignoring because there is very small drop. So basically, if this is roughly equals to V1 only. Okay, sorry. Yeah, this is roughly equals to V1 only. So this is the voltage and this is the current IO over this whole branch. So V1 by IO will give me what? Z equivalent. V1 over IO will give me Z equivalent. Okay. Also, I know the wattmeter reading WO, that is P core. So there are two components, right? There are two components here of current. One component is for the magnetizing current, IM, another component is the core component, correct? So what I can comment is voltage is constant. So I can say that the magnetizing component of the current will be like my IO will be in phasor IM plus IC, okay? And I know the magnetizing component lags the supply voltage by 90 degrees. So it will be minus J into IM and this will be plus IC angle 0, right? So simply what I can comment is if I know the magnitude of IO, so magnitude of IO I know, okay, magnitude of IO will be under root of IC plus IM square. So it is like a power triangle. So here I have my IM, here I have my IC and here I will have my IO. And this is my phi naught, if you remember, no load power factor, right? So I know that my IM will be equals to what? This is IO, right? So it will be IO sine phi naught, IO sine phi naught, okay? And my IC will be equals to IO cos phi naught. Okay, these are my IO and IC values. So how do I find out phi naught? So I know that I know the voltage, I know the current IO, right? So I know the wattmeter reading. So what is wattmeter reading? Wattmeter reading is simply VIO cos phi naught, correct? So if I somehow this is cos phi naught. So if I divide W wattmeter reading by V into I naught, that will be cos phi naught. So from this particular equation, if I divide the two numbers, that is the wattmeter reading and the product of the voltage voltmeter reading and the ammeter reading, that will give me the power factor cos phi naught. And if I know cos phi naught, I will be easily able to find out IC will be I naught cos phi naught and IM will be I naught sin phi naught, because I will be able to find out the no load power factor angle phi naught. Okay, so that's how we find out the individual parameters. There are other ways as well, but ultimately this will be the best way. You can find out the circuit parameters any way you want, okay, but this is one of the way with which you can find out. So make sure whenever you are performing the no load open circuit test, make sure your voltage, because why is no load test performed? To check the core loss. Core loss is due to the magnetizing current. Magnetizing current is due to the flux. So flux is proportional to voltage by frequency. So of course I want to be in the rated condition, right? So my voltage also should be rated and my frequency also should be rated. Then only whatever losses I will calculate will be rated. Okay, got it? So yeah, that was about the P core, because if you remember in the P core, right, the eddy current loss also is proportional to the flux density, and the hysteresis loss is also proportional to the flux density. Okay, so yeah. So one thing I just wanted to like tell this clearly, that there is no restriction, there is no restriction in performing the test on the HV side. Okay, we can definitely perform the test on the HV side, there is no restriction, right? But like if in the interviewer asks you that why do we perform the test in LV side, so like we cannot perform the test in HV side, we can definitely, but the reasons that I gave you, right, these were the reasons, because due to this, the if I perform on the low voltage side, I will require low rating of voltmeter, low voltage of supply, so making the test much easier and simpler. So that is the only reason. that I provided. So there is no restriction. We can perform the open circuit test anywhere we want, but we perform in the low voltage side because cost will be lower to us. Okay. So yeah, I hope you have understood this basic point. That's how we will calculate the values. Okay. So yeah, now like few interview questions. I will come to few interview questions. This is the first interview question. Why the test is conducted at rated voltage and frequency? I already discussed that hysteresis loss is proportional to the flux and flux raised to power x, and the eddy current loss is proportional to bm square f square. So if f is not rated and if bm is not in its optimal value, then obviously the losses also will not be at optimal value. And I want to calculate when actually the losses will be at their optimal value at their rating. So of course the voltage and frequency both should be rated, that I had already discussed previously. Okay. So the circuit parameters can be calculated even if the voltage is not rated, circuit parameters can be calculated. That is, so my Rm and Xm can be computed even if my voltage and frequency are not in rated condition, are not in rated condition, but but core loss, core loss to calculate core loss, to calculate core loss, voltage and frequency must be rated, because I want to calculate the core loss in the rated condition, right? Because I want to calculate the efficiency. So if I want to calculate the efficiency, their P core will be there, right? So for that it must be rated. Okay, got it? So yeah, that was about the this thing, that was about the open circuit test, and few more interview questions are there like this. What happens if open circuit test is conducted at low frequency but constant voltage? So if I conduct the open circuit test at low frequency but constant voltage, then the flux density will increase. If the flux density increase, it will show higher core loss, right? Actual core loss won't be that high, but it will show higher core loss. So of course we don't want to overestimate. Okay, it will not it does not, wattmeter reading does not represent normal operating conditions. Okay, so that is another problem. Also the magnetizing current also will increase. So if flux, right, flux is greater than the flux rated, so I know according to BH curve that B is proportional to flux and here H is proportional to current. So this is my graph. So if flux has increased, that means if I am initially here, now I am here, right? So flux has increased, so that means the current also will increase, right? Current also will increase. Okay, the magnetizing current required also will increase, so my Im will increase basically. And if Im increases, the ammeter reading also will increase. So wattmeter reading will increase and ammeter reading also will increase. Okay, so yeah, this was about that. Now in the open circuit test, this we have already previously discussed actually about the separation of losses, right? We had already discussed that our iron losses can be specified like graph like this. It is P core divided by F, which will be a straight line, but this slope will give me the eddy current constant, and this intercept, y intercept, will give me the hysteresis hysteresis constant. So slope of the graph, this we had already learned in the losses topic, right? Slope will give me the eddy current constant, and the y intercept will give me the hysteresis loss constant. Okay, loss also known as loss coefficient, that also you can say. Okay, now let's discuss about the short circuit test. So what is short circuit test? So short circuit test is actually used to determine the full load copper loss at rated current. So to find out the full load copper loss, what do I need? So what is PUCL? PCUFL? PCUFL is IFL whole square into RO1. So I need to pass full load current. There is no condition for rated voltage, right? I don't need to pass rated voltage. I just need to pass full load current. So in the circuit I need to pass full load current. So what I will do is I will short the secondary. I will short the low voltage winding. I will short the low voltage winding. I will explain why I will short the low voltage winding. Okay. So what I will do, this will be the low voltage winding, and I will short the low voltage winding, and I will apply some voltage here on the HV winding. And actually I don't need to apply rated voltage. Why I don't need to apply rated voltage? Because here if I short it, the induced EMF will be 0. So here also the induced EMF will be 0. So the voltage applied in the primary will be the only the voltage drop in this whole combination. That's it. That's it. Because here the induced voltage is 0 only, right? So the voltage that I need to supply is only this amount of voltage. So that's a good thing. That's why we short it basically. That is the reason we short it. Because for full load copper loss, mainly what is important? The current should be full load. Voltage they have not shared any condition. In case of coal loss, the coal loss depends on the flux density and frequency. So that's why flux density needs to be rated. That's why the voltage and frequency must be rated in that case in the coal loss. In short circuit loss, the full load copper loss is only dependent on the current. Okay, RO1 is just a constant number, right? It is only dependent on the current. So I have to pass full load current. So that is the advantage basically. So overall, this will be my PCUFL. And now one question you might have, okay sir, this I1 is basically I1 full load, you are passing full load current. So my copper loss will be basically what? Copper loss PCUFL will be I1FL square into R01. That is the R01 is what? R01 is basically R1 plus R2 dash. All this is fine. Why are you doing this in the high voltage, sir? Why are you doing this in the high voltage? Why not low voltage? So what are the ratio? So if you remember, if let's say N2 is greater than N1, that means the secondary is high voltage and primary is low voltage. So I know V1 by V2 will be N1 by N2 will be equals to I2 by I1. So the side in where the voltage is rated, that is V1, or let's say the side where the voltage is rated, that is V2, and it is highest voltage HV winding, in that side the current will be lower because KVA must be constant, right? KVA V1 I1 will be equals to V2 I2. So if my sole purpose is to pass the rated current, and if I do this test on the LV winding, I will have to pass more current. I will have to pass more current. So in this, let's take few numbers. So let me take few numbers. Okay. So let me take that my V2 is 200 volts, V1 is 100 volts, and rated. So what will be the rated current in the secondary? Rated current in the secondary will be, let's assume it has to be 10 amps. So rated current in the primary will be what? The ratio will be 2. It will be higher here. It will be 20 amps. Okay. So if I performed this on the HV winding, then I had to pass more current, right? So I will need higher rated wattmeter. Okay. I will need higher rated wattmeter. But here, right, I will not need higher rated wattmeter. Okay, I will not need higher rated wattmeter. If I perform this, I will only need the wattmeter rating must be wattmeter not wattmeter rating, sorry, high rated ammeter. But here if I perform, the ammeter rating will be around like 12 ampere, something like that. So I save on cost. and of course I don't have to pass that much huge amount of current, I have to pass low amount of current. So that is the advantage basically. That is the only reason we choose the high voltage side to perform the operation. In open circuit test we chose the low voltage side, in short circuit test we choose the high voltage side. Okay, so the applied voltage is low because under short circuit condition impedance is very small. So these are the only impedance, right? This voltage drop will be very small because R2 winding resistance is low, leakage reactance also is low. Mainly the core resistance and magnetizing reactance will be high, but these are automatically shorted. Okay, so iron losses will be negligible because here here, right, no current will flow, all the current will flow through the short circuit basically. No current will flow through this, all of the current will flow through the short circuit. Okay, and also one more thing, that this voltage, right, is V1, and V1 is already very low voltage. If V1 is very low voltage, I know the core loss, right? Core loss, if you remember, P core is basically V1 whole square divided by R. So if V1 is very low, then my core loss also will be very low, negligible, very negligible core loss. So it is just vice versa. In case of open circuit test, the copper loss was very low. In case of short circuit test, the core loss will be very low. So we can neglect those and easily find out the copper loss and the core loss, full load copper loss and the full load core loss. And if I know the full load copper loss, you will be able to find out everything else, right? You will be able to find out every single thing. If you know the full load copper loss, if my loading fraction is X, the copper loss in X load will be X square into PCUFL. This we have already learned. Okay, so these are the points that is written over here. So this was the circuit diagram. So yeah, now I hope you have understood. One more thing is that never apply rated voltage when the other side is short circuited. What do I mean by it? So let's say this is my transformer. Okay, this is my transformer, and other side is short circuited. So this LV winding is short circuited, and here I am applying rated voltage. So let's say rated voltage is, this is 100 volt. Okay, sorry, this is V1 side, right? So it is the HV side. HV side is 200 volts. So I am applying 200 volts here, and let me assume few numbers. Okay, let me assume that R1 is 1 ohms, JX1 is 1, J1. Okay, this is 1, this is like, this is also 1, and this is also J. So what is happening? So the rated current is 10 amperes, what I discussed, right? Rated current will be 10 amperes. But what is happening, if this is short circuited, what will be the current? Current will be the voltage upon impedance. Voltage upon impedance. So impedance is this R1 plus R2, that is 1 plus 1, that is 2 plus J2. Okay. So if I calculate the magnitude of the current, this will be 200, like 100 divided by root 2 basically, correct? Huge current, huge current. So my rated current is 10 amperes, but right now huge current is flowing, almost 70.7 amperes. So the key point is, never, like if you are doing performing the experiment and if you are performing short circuit test, never apply rated voltage while performing short circuit test. Else what will happen, winding will get burned because huge current will flow. Otherwise winding will get burned. Okay, so always apply low voltage while performing short circuit test. Okay, so how do we do? Basically we have this auto transformer through which we actually just slightly, not auto transformer, yes, yeah, auto transformer only, if you have done the experiment. So slightly we increase the voltage, and after slightly increasing the voltage, as soon as I see in the ammeter that rated current is flowing, that is the end. Okay, that is basically the what do you call, that is basically the condition, the copper loss, all the conditions, right? So let's go to the circuit diagram now. Okay, let me go to the circuit diagram of the test. So this is here, this will be here, okay, here. So this is basically the circuit diagram. So I have a wattmeter here in the high voltage side. In the high voltage side I have a ammeter. Okay, so basically, right, if I use the circuit diagram and use this, so if I just write it here and copy this circuit diagram here, so what I can say is that what will the wattmeter measure? Wattmeter will, like, ammeter will measure the short circuit current. Voltmeter will measure the this short circuit voltage. Okay, so this will be the voltmeter, ammeter, and wattmeter will measure the copper loss, because whatever loss is happening, this is due to the resistors only, right? So wattmeter will measure the copper loss, PCU FL, full load copper loss. Okay, so these are the readings of the meters. And how can I find out the circuit parameters, like the resistor and the this leakage reactance? How will I perform the resistor and leakage reactance? Okay, so for this you can very basically, so I know what is my Z01. Z01 will be what? VSC upon ISC, right? Z01 is the overall referred impedance, like impedance referred to the primary or the high voltage side. Impedance referred to the high voltage side. So this is my Z01. Also I know this thing. So if my Z01 is here, so my R01 will be here, that is R1 plus R2 dash, and my XL will be somewhere here, right? This will be my JXL. Okay, so my Z01 will be the combination of these two, right? So this is the angle phi SC, actually phi SC. This is the phi SC angle. So if I want to calculate R01 and all these things, right? So I know this thing, wattmeter will read the copper loss. So wattmeter will read ISC whole square into R01. So from there I can easily find out what is R01. So R01 will be wattmeter reading divided by ISC whole square. If I know R01, I know Z01, so I can easily find out XL, right? What will be XL? XL, actually this should have been XL01. So XL01 will be basically under root of Z01 whole square minus R01 whole square. Okay, like this you can find out. And if you want to refer to the other side, you can simply refer to the other side using the turns ratio. Okay, that is fine. I hope these things you remember. And if I know the full load copper loss, this is PCO full load, I will be able to find out the copper loss in any load, right? So copper loss in any load, PCU will be what? PCU will be X square into PCU FL. All this we have discussed previously very well. So this is how you will find out the circuit parameters. So these circuit parameters, for finding out the circuit parameters, you actually don't need to pass the rated voltage and rated current. Any voltage and current if you pass, if you take the ratio, you will be able to find out the circuit parameters. So make sure the current, like the connections are proper. Okay, got it? So that was about the short circuit test. Okay, so if you ever want to refer the test data from one side to the other side, so let's say there is a question, how can we refer the test data from one side to other side? So referring of test data, let's say you have performed open circuit test in the low voltage winding, but you want to find out the values in the high voltage winding. What you will do? It's very simple, right? I can simply refer the voltage, how that like in test, what is the test data? Test data, there are mainly three instruments: voltage, current, and power. So how are voltage, how is, like, this is my data, right? Test data. So how is voltage scaled? Voltage, right, referred will be what? Turns ratio. Simply it will be turns ratio. So voltage and current will be referred according to turns ratio, and the power, right, power of remains same, power will not change. Wattmeter reading, this is the wattmeter reading W. So wattmeter reading remains same because power does not get referred, it is constant throughout the primary and secondary. So power or wattmeter reading, this is the point 1. Point 2 is wattmeter reading remains same. Okay, it will not change on both sides. So why is the, like, few interview questions again, why is the short circuit test performed on the like this should be, why is the short circuit test SC test performed on the low voltage side? Reason you already know, I have already discussed, so I will not explain here, that is written over here. Why is a low voltage applied? Again, the drop will be very low, although rated current is flowing, but the impedance is very low, so the drop will be very low. That's why I don't need very high amount of voltage to pass high amount of current, as the impedance is very low, so low amount of voltage will pass high amount of current. Generally it is 5 to 10% of the rated voltage. The voltage that I need to apply is 5 to 10% of the rated voltage. Okay, so yeah, I hope you have understood this point. Now what if the short circuit test is performed in a load that is not rated? What will happen then? My wattmeter reading, that is PCU, will be equals to what? It will be x square into I square IFL whole square into R1. So basically it will, like, whatever reading I will get, it will be this value. I will know what is the loading, amount of loading. So from this, right, I will be easily able to find out this is equals to x square into PCUFL. So from this I will be easily able to find out what is my PCUFL, because I know what fraction of loading I am applying and I know my wattmeter reading. So if I divide my wattmeter reading divided by x square, that will give me the full load copper loss. So even though I am not actually operating in the full load, I am not sending full load current, I will get the full load copper loss, but there can be errors in the reading. Okay, just be careful. If I don't operate in the rated voltage, there can be minute errors, right? Errors due to which the results will not exactly match. So it's best to perform on the rated condition only for the copper loss. But you can do this as well, simple mathematical trick. But mathematically this will work. Experimentally, if I do this in real life, there will be errors, right? There will be errors due to which the full load copper loss will come out to be a different value than the actual one. There can be error of 5 to 10%. Okay. Now one more interview question is that what happens if short circuit test is conducted at constant voltage but lower than rated frequency? So if the short circuit test is conducted at constant voltage, that is fine, VSC, but I am operating at a lower than rated frequency, then I know my leakage reactance XL is 2 pi FL. So leakage reactance, although L is same, right, this F will reduce. If F reduces, XL reduces, and if XL reduces, that means the total impedance reduces. So if the total impedance reduces, the current will increase, right? So if I am giving same short circuit voltage and overall impedance reduces, that means the overall current will increase. That's it. Okay, so this can lead to inaccurate loss measurements. Here as well, same thing. This, although this is totally allowed, you can do it, but this may lead to inaccurate test results. Okay, same thing here. So yeah, I hope you have understood this basic point. Also the power factor also increases, so that is also another point, because the what is the power factor? Power factor is cos phi naught, that is the wattmeter reading upon the V SC into ISC, right? So basically if this XL reduces, if XL reduces the power factor angle, what will happen? The power factor will be better, so cos phi naught will increase basically, because the imaginary component is reducing. Okay, so yeah, that was about it, about the different kinds of tests. So open circuit test is conducted at rated voltage frequency, and it is measured in the, generally it is performed in the low voltage winding. Short circuit test is conducted at reduced voltage but rated current to measure copper loss, and it is performed in the high voltage winding. So it is used to measure the shunt parameters. So those coal loss component parameters are also called shunt parameters, and these are called series parameters. So it is performed in high voltage winding. Frequency variations affect reactance, impedance and loss measurements, leading to inaccurate calculation. So it is always good to perform the test in the rated frequency. Okay, so now I will give you few questions as homework, and in the next lecture we will solve all these questions. This is the first question, this is the second question, okay, third one, fourth one, fifth one, that's it. Okay, so I hope you enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down below, and make sure to comment in the first video. I just repeat because marketing karte rehna padega. Okay, so thank you for watching, and I will see you in the next video. Until then, happy learning.